So we've been talking about describing the motion of an object, namely the position, the velocity, and the acceleration. Today I want to focus on motion in one dimension, so an object moving in a straight line, for example a car driving on I-70 through Kansas. In this situation, if I want to describe the position, I just need a single variable. For my example of a car, if I tell you what mile marker I'm at, then you know exactly where I am. So we can describe the position with x, and that's what you'll see most frequently in this course. However, it could also be y or z for that matter. Similarly, to describe the velocity, I only have a single component of velocity. How fast is it moving in the x direction? So the velocity is the x component of velocity, and the velocity is related to the position by the derivative of the position is equal to the velocity. Likewise, the acceleration is the derivative of the velocity, or the second derivative of the position. And we don't need to stop there. We could talk about the change in acceleration with respect to time. That's actually a quantity that's called jerk, because jerky motion is motion where the acceleration changes rapidly. But the relationships I want to focus on here are that the velocity is the derivative of position, and that the acceleration is the derivative of velocity. Now these relationships are pretty straightforward. If I wanted to find the velocity or the acceleration, let's say, if I knew the position as a function of time. So if I knew where the particle was at any given time, let's say it was given by this relationship x of t equals t cubed plus 2t squared minus 7t plus 5, it would be pretty easy for me to calculate the velocity. All I would have to do is take the derivative of this expression, which would give me 3t squared plus 4t minus 7, plug in the time I'm interested in, and I could find the velocity. Similarly, to find the acceleration, I could take the derivative of the velocity and find that it's 6t plus 4. These relationships aren't so useful, however, in a situation that we're going to be much more likely to run into in this course. Namely, if I were to give you a constant acceleration, tell you an object has an acceleration, let's say, of negative 9.8 meters per second squared, could I then calculate its velocity and its position? And the answer is that I can, but it's not so obvious from this relationship. So instead of knowing x and finding v or a, I'm saying if I know a, what is v or x? And I need to go through sort of the opposite process of what I just did. The acceleration is the derivative of the velocity, so if I have the acceleration, I can get the velocity by taking the antiderivative, or the integral. So to solve this equation for v, I'm going to bring the dt over to the other side of the equation and integrate. We'll see that I have the integral of dv is equal to the integral of a dt. And here's where the constant acceleration is so important. If the acceleration is a constant and doesn't depend on time, then I can pull it out of the integral and get the integral, or a times the integral of dt. Integrating this, I get v of t is equal to at, and of course I need a constant of integration. Now that constant could be anything, which means that right now I don't have a really good handle on what the velocity is if I know the acceleration, so I need to figure out what that constant that I'm adding is. And the way that I can do this is to take this relationship that we've established and pick a specific time. So this relationship's true for any time, which means it's true for t equals 0. For example, when I start my stopwatch or at the beginning of the problem. And if I plug in 0 for t, then I see that the velocity at t equals 0 is equal to a times 0 plus the constant. Now this velocity at t equals 0, we're going to denote with a slightly differently, the v with a little subscript of 0 that we'll call v naught. Now we can see that since a times 0 is 0, that my constant is simply v naught, or the initial velocity, the velocity that I was given for t equals 0 in the problem, let's say. Plugging this back into the top equation, I find a full expression for the velocity as a function of time. V is equal to v naught plus at. Similarly, I can calculate the position as a function of time if I have a constant acceleration by noting the relationship that velocity is the derivative of the position, and proceeding as I just did in the previous example. So I'm going to bring dt over to the other side and integrate. And I want to emphasize again that v naught is a constant. V changes, but v naught is actually the velocity at the beginning of the problem, at the time that we've said is t equal to 0. So that can come out of the integral, as can a, because again we're insisting on constant acceleration. And what I find is that x is going to equal v naught t plus 1/2 at squared, and again plus a constant of integration. So now once we're able to determine the constant of integration, we will have an expression for the position as a function of time as well. To do this, we're going to carry on just like we did in the previous example and say this expression is true for any time. So I'm going to pick the time t is equal to 0. And in doing that, we see that x at t equals 0 is equal to v naught times 0 plus 1/2 a times 0 squared plus the constant. And as we did with velocity, we're going to call the position at t equals 0 x naught. Plugging this back into our original equation at the top of the slide, we see that x is equal to x naught plus v naught t plus 1/2 at squared. So just starting from an assumption that we have constant acceleration, which is a situation we'll see frequently in this course, we now have equations that tell us both the position and the velocity as a function of time, and these are known as the one-dimensional equations of kinematics. So the position is given by x naught plus v naught t plus 1/2 at squared, and the velocity is given by v naught plus at.